Avalanche, but not the snowy kind you're thinking of. Today, we're diving into the fascinating world of avalanche effects in diodes, a phenomenon that's as electrifying as it sounds. Let's start with the basics. In a typical diode, we have what's called forward biasing. That's when the positive voltage is connected to the anode and the negative to the cathode, allowing current to flow through the diode. Simple enough, right? Now flip the script. In reverse biasing, the positive voltage is connected to the cathode and the anode is often grounded. Under normal circumstances, this setup looks like an open circuit, nothing happens. But there's a hidden threshold known as the reverse breakdown voltage, or V_BR, and that's where things get interesting. There are two main phenomena during reverse breakdown: Zener breakdown and avalanche breakdown. When the breakdown voltage is above about 5.5 volts, we're usually dealing with an avalanche diode. So what makes a properly designed avalanche diode special? It's all about preventing hotspots. By ensuring the current density is uniform across the junction, we avoid areas where large currents could build up and damage the diode. This uniformity also keeps the breakdown voltage nearly constant compared to non-avalanche diodes. You might be wondering, how does a Zener diode compare to an avalanche diode? While they share similarities, the effects responsible for their behaviors differ. A Zener diode has a voltage higher than breakdown and exhibits a negative temperature coefficient. Its breakdown voltage decreases as temperature rises. An avalanche diode, on the other hand, has a small positive temperature coefficient. Its breakdown voltage increases slightly with temperature. One of the standout features of avalanche diodes is their ability to clamp voltage spikes. Often referred to as clamping diodes, they begin to conduct at a specific voltage, preventing the voltage from rising any further. This makes them excellent for surge protection. However, they're limited by the amount of energy they can absorb, so good heat sinking is crucial to prevent overheating. But the avalanche effect isn't just limited to diodes. Enter the single photon avalanche detector. Imagine detecting a single photon. These silicon avalanche photodiodes are reverse biased near their breakdown voltage. When an incoming photon generates an electron-hole pair, the high electric field amplifies it into a measurable current. It's fascinating how a single photon can create such a significant response. And it doesn't stop there. Avalanche transistors, essentially bipolar junction transistors operated beyond their collector to emitter breakdown voltage, can switch very high currents with transition times less than a nanosecond. Legendary engineer Jim Williams found that many high-speed 2N2369 transistors could produce avalanche pulses with rise times as fast as 350 picoseconds using a 90V power supply. So what's the big takeaway? Understanding the avalanche effect unlocks new possibilities in electronic design, from enhancing surge protection to exploring ultra-fast switching. Keep this phenomenon in mind the next time you're delving into circuits. You might just spark an avalanche of innovation. Now, for a quick brain teaser, why did the electron get so excited at the diode party? Because it broke down and went into avalanche mode. Thanks for joining me on this electrifying journey through the avalanche effect. Stay curious and keep those electrons flowing.